If I were to summarize what makes a good problem, it should just be beyond your current range of capability. It should have maybe just one difficulty that you don't quite know how to solve, but every other aspect you have some idea of how to proceed. Hopefully the question has some connection to some intuition that you already have. So like many questions have a geometric flavor, and so you can use your spatial intuition. Some people are naturally very good with numbers, and so actually having a question with a lot of numbers in it, you can leverage your intuition. So it has to match your skill set. And it's not so much whether you succeed or fail at the question, but it's whether you can learn something from it. The ability to ask the right question and to frame it in the right way, I think, shows up all over human endeavor, not just in mathematics. Just to give you one example, there was this airport that had received a lot of complaints about people having to wait for their luggage to arrive. So they tried to solve the question of shortening the time between the landing of the plane and the deploying of the baggage. But they found that the solutions they implemented didn't decrease customer complaints that much. And it turned out what they really didn't like was waiting at the carousel for the luggage to arrive. And actually the solution was to take longer to walk from the airplane to the luggage carousel. So they put some partitions so that they would feel like they are making more progress. And by the time they arrive at the carousel, the luggage would arrive shortly afterwards. And this reduced the complaints by quite a bit. So it is possible for your thinking to get stuck in a rut. You are so certain that a certain approach is going to work or a certain answer is going to be what you expect. So sometimes it's asking the right question and is key to actually getting a satisfactory answer. You don't want a problem that is too easy, that is too routine. You always want problems that are just barely out of reach of the known technologies. One analogy that many mathematicians use is to liken mathematical problem solving to climbing. In fact, many mathematicians are rock climbers. I myself am not, but many of my friends are. And actually, rock climbers, they use some of the same language that mathematicians use. A difficult cliff is called a problem. And when you climb the cliff, you solve the problem. If you want to get from the bottom of a cliff to the top of the cliff, and it's 30 feet high, you can't just go directly up there. That's not feasible. But you want to find some handhold or some ledge which is more feasible, just almost within reach. You just need to stretch a little bit. And then once you're at that point, you identify the next step, which is gets you closer to your goal, but one which is just barely within reach. Even the best rock climber, there will be certain cliff faces that are just not climbable, even with the best tools and the best physical training. And that's okay. In mathematics, it's okay if you can just get some new progress that is just a little bit above what previous climbers were able to reach. And then the next person, maybe someone younger and more energetic, or just someone with a different mindset than you, can go and take the next step. It doesn't matter if you fail 9 times. If you make partial success one time, and you can explain that success to someone else who can take it to the next level, that's how mathematics proceeds. You have to learn to be, part of a bigger process that's been going on for thousands of years. And we have the advantage over climbers is that, it's okay to fall. You can just start over. So you can take some risks that you wouldn't normally do if you actually had to climb a cliff. It often happens that a really complicated problem can be broken up into bite-sized pieces, and each piece is manageable. One historical example of a complex problem that was solved by breaking it into smaller parts was the problem of determining the orbit of the Earth and Mars around the Sun. So in the 15th century, I believe, Nicholas Copernicus famously theorized that the Earth and Mars and all the other planets went around the Sun, the so-called heliocentric model. Previously, it was thought that the Sun instead went around the Earth. He, in fact, theorized that the orbits were perfect circles. And that was approximately correct, but it didn't quite match the observations. Copernicus was also able to determine the period. He was able to work out that the Earth went around the Sun once every year, 365 days. Mars, for instance, took a little longer. It took 687 days to go around the Sun. So that was correct. The periods were correct, but the orbits were a little bit off. Johannes Kepler, a few centuries later, had realized this, and he used the most precise measurements of the planets at the time to try to figure out exactly what the orbits of Earth and Mars were. He knew they weren't circles, but he couldn't figure out exactly what shape they were. He knew about the technique of triangulation. So triangulation is an old navigational technique. If you're at sea and you can see two landmarks, and you can measure the angle, the direction to each of these two landmarks, you can draw a triangle, and then you can place on your map where you are. So in order to locate the Earth, he wanted to use the Sun and Mars as landmarks. But the whole problem was that we only had one fixed landmark, the Sun. And Mars also moved, and Kepler did not know what the orbit of Mars was either. But what Kepler realized was that he could reduce the problem to a simpler problem. So if Mars was fixed, if Mars didn't actually move, then it could be used as a landmark, and you could use triangulate from the Sun and Mars. And Copernicus had already worked out that every 687 days, Mars returns to its original position. So Kepler's idea was to take the measurements of Mars and the Sun that were available, but only sample them in spacings of 687 days. So he took measurements that were 687 days apart. For those particular sequence of measurements, Mars was in a single location. And so Mars was effectively fixed. And then it was a landmark that you could use to triangulate. And he was able to use that to first work out the orbit of the Earth. And then there's a way to go backwards. Once you know the orbit of the Earth, you can work out the orbit of Mars and the orbit of the other planets. And he eventually discovered what we now call Kepler's laws of planetary motion. For example, he discovered that, in fact, all the planets move in ellipses. But the key idea was to reduce a difficult problem when everyone was moving to a simpler problem where you had fewer moving parts. One example of breaking up a complex problem into simpler parts is the story of group testing, which was a technique developed in the 1950s. The US Army wanted to test soldiers for a certain rare disease, and there were blood tests available, but the blood tests were in limited supply. So there was not enough tests to test all the soldiers individually. The solution they came up with was to take blood samples from many different soldiers and mix them together, so that if there was a positive test there, that would mean that someone in that group had the disease, and if it was a negative test, it meant that nobody in that group had the disease. The mathematical problem was what is the least number of tests you would need in order to determine who had the disease and who hadn't. Now, this problem is complicated because there are so many possibilities. Maybe there's 100 patients or 100 soldiers, and maybe one of them has the disease, maybe two, maybe three, we don't know. But you can start by simplifying the problem. Suppose that exactly one person had this disease and no one else did. Then how can you isolate this one person out of 100, let's say? So we're going to demonstrate how group testing works, and we're going to demonstrate this visually using ping pong balls. So instead of 100 soldiers, we will have 100 ping pong balls, each of a number. This is the 89th soldier. And one of the balls has a little rattle in it that will make a noise, representing the fact that that is the patient with the disease. So you can hear it if I shake the whole box. Okay, there's a little rattle you can hear. And the way we're going to test for this is that we will take several of the ping pong balls and put them in a jar like this to represent the mixing of samples. So it turns out that the correct thing to do is to split the sample into equal portions, 50-50, and just test one batch of 50 at a time. Okay, so we have divided now our population into two groups, the balls from 1 through 50 and the balls from 51 through 100. And we're going to test the balls in this sample. And one or two things will happen. Either I will hear a rattle, which means that the infected patient has a number between 1 and 50, or I will not hear a rattle, in which case the infected patient must be in the other group. But in either case, I will have cut down the number of possibilities from 100 to 50. I'm going to shake this. Okay, and I heard a rattle. So the patient is somewhere in this group, and I can eliminate all the patients from 51 to 100 and only now work with this group. Okay? So that is how we use our first test. And now we can just repeat the process. We're going to divide up this population from 1 to 50 into 2 equal portions. Now we're going to use 1 to 25 and 26 to 50. So now we're ready for our second test. Okay. There was no rattle, so the test was negative. And so therefore, the infected soldier must be in the range 26 to 50. We have eliminated the first half, 1 through 25. So now we can repeat the process with our new population from 26 to 50, and we will again subdivide into 2 equal populations. I hear a rattle. Now for our fourth test, we're going to subdivide our population from 26 to 31, 32 to 37. Okay. No rattle. Fifth test. There's a rattle. Now test number 6, I'll divide into 32 and 33 and 34. There's a rattle. I have eliminated 34. Finally, test number 7, I just test each one of my 2 remaining subjects, 32. Okay, and there is no rattle. So after my 7th test, I have concluded that the infected patient is patient number 33. Okay, so after 7 tests, we have found that the infected patient is patient number 33. All right, so we have seen that in this particular case, it only took 7 tests for us to narrow down the infected patient to a single candidate. And that turns out to always be the case, that if you start with 100 patients and you know that exactly one is infected, it will always take at most exactly 7 tests before you are guaranteed to isolate the patient. And that's what you do when there is one infected patient.